like to thank the organizers for this opportunity to bring to you some of the research we are doing in Brown University. Well, it's a bit embarrassing for me because this session is about solar cells and I'm going to talk about AULAs. Well, the title of my presentation is New Deep Blue Emitting Copolymers for Polymeric Light Emission Diodes. Well, I cannot start my presentation but without mentioning the recent award of the Nobel Prize in Physics to these three Japanese physicists, Isamu Akasaki, Hiroshi Amano, and Tsuji Nakamura, for the invention and development of the blue LEDs. Well, this is quite important and has a big repercussion in our society because this type of devices allow to save a lot of energy. So the LEDs, they can save up to 15 times more energy than the incandescent conventional bulbs, or even 4 times as efficient as the fluorescent ones. Even more, they last longer. The life expectancies they are like 10 times more efficient, they last 10 times more than the incandescent bulbs, that an average lifetime is just 2 years. So, what do we need for having lighting or a display? The first thing we need is having 3 different emitters with 3 primary colors, red, green, and blue. Well, this has already been solved in organic LEDs, but in our case, which is the organic ones, this has only been solved for, having efficient LEDs or LEDs, it's only been solved for red and green LEDs. They have already achieved the maximum theoretical quantum efficiency, which is 20%. But as you can see here, the blue ones, this is not blue. This is what is called sky blue. So where is the problem arising from? As you can see here, this is a plot. You can assign to every color. You have an X and a Y coordinate. So you have green, red, and blue. And where is our sky blue line? Sky blue is lying somewhere in between the blue and the green. So it's not actually blue. Well, this is the sketch of an OLED. So you have an emissive organic material, which is sandwiched in between 2 electrodes. So upon the application of an external bias, you generate a lot of excitons. And then these excitons, they diffuse to the emissive material, they recombine, and then you have light. The first problem in these materials arise from the generation of the excitons. Upon all the excitons you generate, just 25% of the excitons, they are singles. And this is quite a problem for organic materials. As most of the organic chemists know, organic materials, they have really big problems in emitting from triplet states. It's not a pretty efficient mechanism of emission. So how do we solve this? Well, pretty easily. We can have metallic dopants like platinum or iridium that by heavy atom effect, they can gather all these triplets and convert them into light. But again, the problem is still in the blue, because this problem solves all the problems for red and green, but not for blue. Why is this? Well, this is the typical blue-emitting iridium complex. This is called FIRPIC, and the color is pretty much like this sky blue you can see here. The problem with blue light is that blue light is quite energetic, and so the first problem we have is that we have long-term stability issues. Another problem is that to match this high gap energy, this is blue, so we need to have a polymer or a material where to embed this dopant, and the energetic levels of materials, they have to be similar. This is quite difficult. So when we got to this point, we thought in our group, okay, when we just remove all these metals, we forget about the triplets, we are going to operate in a fluorescent only mode. And obviously, we are going to be to a maximum efficiency, theoretical maximum of 5%, but our displays, will enjoy a greater color contrast and a wider color gamut. And also, the illumination, we are going to enjoy better color rendering and higher color temperature. So, it might worth to waste some energy, wasting it into triplet excitons, so we can get a better experience with our displays or having a warmer lighting. Well, how do we put organic materials to shift their emission into the deep blue? Well, the most typical strategy is to disrupt the electronic communication between the different moieties of our molecules. So we can achieve it by following different strategies. The first strategy we follow is to introduce very bulky side chains into some units so that we induce a torsion in the angles between the different aromatic moieties. So we disrupt the communication between the moieties. Another strategy we can follow is metaconjugation. As most of the organic chemists know, metaconjugated systems, they are worse communicators of electrons than the ortho or paraconjugated ones. So this is another tool we can employ in our systems. And finally, we can try to understand which is the minimal domain, emission domain in our systems necessary for emission, and try to isolate them within the polymer. So we develop different families of polymers employing these tools. So the first family, we employ this metaconjugated fluorine along with dibenzoyl dioxide with pretty bulky side chains and use a torsion. The first thing we observe is that we have a nice emission peaking around 415 nanometers. And we can observe from this, varying the amount of metaconjugated fluorine versus the dibenzoyl dioxide, that the most important thing here is the metaconjugation. So it doesn't matter how much torsion is induced with the bulky side chains, the important factor here is the metaconjugated. So this is how we characterize our devices. So we have pretty good color coordinates. This is the blue. And well, the efficiency is not bad. It's 2.7 external maximum efficiency. But the brightness of our compounds is not good. Our finest polymer here just has a bigger 37 candela per square meter. Well, this is not even necessary for display purposes. For display, you normally need at least 100 candela per square meter. So we decided to completely remove the metaconjugated and go for straight conjugated para fluorine, and we varied the proportions between the fluorine and the dibenzoyl molecules, and we did varying also the bulky side chains. The first thing that we observe is that the emission is completely redshifted up to 14 nanometers. And also here, obviously, the determining factor in the blue shift is the amount of S units, the one that induce the characteristic in our system. So the more S, the more blue shift. I have to say the shift is not big, it's just about 5 to 10 nanometers. Well, so these are our polymers with the results. This is one of actually it's the finest one of the series. The emission is peaking at around 450 nanometers with good color coordinates. And we find out that the best polymers are the ones that they have 75% content in fluorine. And when comparing the 75% which are P5 and P7, the best performing one, is the one with the bulkier side chains, which is P5. So here we have a 3.2 maximum external quantum efficiency with pretty low terminal voltage, and also with a pretty good maximum brightness, which is 2500 candela per square meter. This is good even not only for display purpose, but also for lighting. For lighting you need around 1,000 candelas per square meter. Well, this solid family, we just have metaconjugation. We have a paraconjugated fluorine with a metaconjugated carbazole. Well, these are just preliminary results on these materials. These materials, they are pretty blue. They're quite blue, pretty close to the violet. Well, the brightness is quite good. It's 100 candela per square meter. And also it has pretty low turn-on voltage, but the maximum external quantum efficiency is just a meager 1.5%. Well, finally, the sodium this family of materials. Here, we were successful identifying which is the minimal emissive domain for having emission. So, we think it's having around like 3 biphenyl units, consecutive biphenyl units. So in the first case, polymer P9, we have them consecutively linked within the polymeric main chain, and then we stop the conjugation using this biphenyl fluorine with its, with its quaternary carbon, stopping the conjugation. And then in this other example, P10, we have the minimal emissive domain isolated from the rest of the main chain, which goes along this way, as a pendant group. So this domain is 2 carbazoles and linked to the fluorine. Well, this material there also, as you can see, the color coordinates is 0.16, 0.07, 0.06. This is not even blue. This is actually violet. Well, there are just very few examples of polymeric materials having such a blue-shifted emission. And also, the external quantum efficiencies, they are quite high. In the case of P10, which is the finest one, it's pretty close to the 5% maximum theory. The theoretical maximum is 3.9%. Well, they all operate at pretty low terminal voltages, and the maximum brightness is not huge, but it's more than enough for display purposes. Well, as a matter of conclusion, efficient non-doped deep blue LEDs have been fabricated with EQEs close to the maximum 5% theoretical maximum. Expensive and scarce metals have been completely removed from our devices, and also we have proved that our usage strategies they are quite successful in disrupting the electronic conjugation in our materials, so we can push the emission deep into the blue. Well, thank you all for your kind attention, and also our collaborators, my former supervisor, Martin Bryce, and also our physicists, the one making the devices, measuring them, Andy Mogman, Hamid Al-Attar, and Javan Cook, EPSRC for the funding. Thank you very much.